Alternating current. Alternating current, or AC, changes direction, unlike direct current, or DC, that always travels in the same direction. So here we have a much simplified model of two wires, the top one carrying alternating current, and you see the electrons just move back and forth. The bottom one carrying direct current, and the electrons are moving steadily in the same direction. Mains electricity is alternating current and has a frequency of 50 Hz. So as time period is equal to 1 over frequency, this is 1 over 50 Hz, giving a time period of 0.02 seconds. So we can plot a graph of the potential difference against time for the mains, and you see it does one complete cycle in the time period we just found of 0.02 seconds. The mains is quoted as having a potential difference of 230 volts, around about this value. But as you can see, it has a peak potential difference of around 325 volts, going down to about minus 325 volts. 230 volts is what's called the root mean square value, or RMS value, and this is the value of a DC potential difference that would give the same power as this alternating current. Electrical power is given by current multiplied by potential difference, or alternative expressions of current squared multiplied by resistance, or potential difference squared divided by resistance. In each of these terms, the power will be positive, whether the potential difference is positive or negative. The current will be in the same direction as the voltage, and so in this expression, both these terms would either be positive, leading to positive power, or both would be negative, leading to positive power. In this term, if the current is negative, when it is squared, it is positive. Likewise here for the potential difference. So if we plot again the graph of potential difference against time, we could superimpose upon that a graph of the power. You'll see that the power is always changing, but is always positive. If I draw a line across here, this gives the mean power. You'll see, for example, that here where the power is above the mean power, I could take this shape and place it in this gap, where we have a value below the mean power. So we see that the mean power is half the peak power. If we call the peak potential difference V0 and the root mean square value of potential difference V RMS, we can write this expression. So this is saying that the power using the RMS value of potential difference will be half the power using the peak value of potential difference. Cancelling the r's, we get this expression. So the V RMS squared is equal to the peak voltage squared over 2. Or square rooting both sides, we get that the RMS value of potential difference is equal to the peak value divided by root 2. We can now follow the same argument using current. So I squared RMS times R, the power using the RMS value of current, will be equal to half the power using the peak value of current. Again, cancelling by r's, we get that the I squared RMS is equal to the I peak squared over 2, or the RMS current is equal to the peak current over root 2. So for the mains, we've got the RMS value of potential difference is equal to the peak value over root 2. The peak value being 325 volts gives an RMS value of the mains of 230 volts. Let's go through this example. A lamp connected to an AC supply is just as bright as when connected to a DC supply with a current of 2.5 amps. calculate the peak current provided by the supply. Well, we've just found that the RMS current is equal to the peak current over root 2. So rearranging, we find that the peak current is equal to root 2 multiplied by the RMS current, which is root 2 multiplied by 2.5 amps, the AC current which gives the same power or brightness as the DC current we have, meaning that the peak current in this case would be 3.5 amps.